It's fired.
Okay. All right, hi everyone. So today we're going to be talking about dynamic programming on subtrees. So in past weeks, I believe we talked about dynamic programming algorithms, as well as graph algorithms and some things about trees. But dynamic programming in its most general form is actually, you can view it as on a graph. And a tree is a specific example of that. And this technique is very useful, it's very general. A lot of problems where you want to compute things for, let's say, every node on a tree, you can solve it using dynamic programming. So yeah, that's the general topic. And so the problem that we're looking at today is sum of distances in tree. So the problem statement is very simple. You're given a tree of n nodes, and you want to compute for each node, v, find the sum of distances from v to every other node. Okay. And all right. Okay. So okay. So all right. So immediately off the bat, can someone give me like what is a brute force algorithm that you might just think of directly? It doesn't have to have like very good runtime, but
you can do like a depth first search starting at every node.
Yeah. Okay. So yeah. So initial idea is yeah. So you can do a depth first search from each v. Do a depth first search. And so, so along the way, let's say you are at 0, you do a DFS from 0, then you can find what is the distance of every other node along the way in the DFS. And that gives you the answer for 0 after you add it all up. So what would the time complexity be for this?
V plus c squared. I mean, v times v plus c, I guess.
Okay, so we can simplify that. In a tree, what's the number of edges?
Oh, right, it's v minus 1.
Yeah, so
it's v squared, basically.
So here, the runtime is time complexity. Time complexity is O of n squared. Oh, this is not the best one. All right, so that gives us one algorithm. The goal of this lecture is to find an algorithm that does better than O of n squared. All right, so we will come back to this, but first I will discuss sort of a simpler version of this problem, or actually several problems that are sort of simpler versions of this. And they will, and after we solve those, we can come back and they'll actually combine to give us a solution for this. I guess I should write the goal is to find subquadratic runtime. So something like O of n or O of n log n, etc. All right, so I'm going to give a simpler problem first. Count number of nodes in subtree for each node. All right, so the goal here is, let's say we root the tree let's say you root the tree at 0, let's say 0. So then that defines the subtrees for each node. Like, so the subtree for node 2 is 2, 3, 4, 5. Right, now the question is, for each v, find the size of the subtree at v. So for example, in this tree, what would be the size of the subtree at node 2?
3 nodes.
Yeah.
And including itself.
Yeah, let's include itself as well. 4. Yeah. So for 2 it'd be 4. For 3 and 4 and 5, and 1 would be 1. And for 0 it'd be 6.
Right. Sorry, just one quick question.
Yeah.
Are we trying to compute the sum of distances from V to every other node in the subtree, or every other node?
In the entire
okay.
tree.
Yeah.
So, but we will actually solve that problem too, right after this.
Sure.
So after we solve those two problems, we will actually find a way to do this.
Yeah.
And we'll see that thinking about it in subtrees actually gives us it's an easier version of a problem that allows us to think about this, and actually you can combine it back to get that.
Okay.
But first we will do this. So again, you can apply there is a brute force solution which gives you a quadratic time complexity. If you just say you start at each node, you just do a DFS or a BFS to go through all of its subtree and then just find what the size is. But our goal is to find an O of n solution, O of n time solution that actually finds the answer for every node V. So in like O of n, you can actually find all of them.
Right.
Yeah, so the idea is, let's suppose that I have some vertex V. Let's say I have some node V. And let's say that we have, its children. Let's say the children of V are U1, U2, and so forth, and UK. So suppose I have computed the answer for U1, U2, and UK. So let me say that, let's say size V is, let's say this denotes the size of the number of nodes in the subtree. So if I already know the size of the subtrees of each of the children, U1, U2, UK, can you give me, can you express the size of V in terms of those?
Yeah, so it's 1 plus the size of U1 plus size of U2 plus.
Right, exactly.
1 plus, yeah.
This would be 1 plus size U1 plus, yeah. So it would be, yes. And yeah, this formula is just direct because the subtree including V is just V plus all of the subtrees of its children. Okay, so this seems to suggest a solution in recursion. So let's say initial idea, this suggests we should use something called recursion. So recursively, I can write down a function, let's say to compute size of V. Let's say I have a function size of V, where for all U children of V, okay. I guess I'll just say return 1 plus the sum of size U. Okay. All right. So that gives us a simple way to do this. And so I guess there's also a base case, which is the base case is already if there's no children, then you just return 1. It's a leaf. Okay, so suppose I called the root. So let's say I called size 0. What would be the runtime of just this simple recursive algorithm? So I call size of 0, and it recursively computes it.
OV.
Okay, so I guess I should say that this size of u is just a function call to size. We're not storing anything here. There isn't an array.
Right.
Okay.
But
All right. So let's see what happens when I call size of 0. So first I would call size of 0, and then it would look at size of 1. Okay, and then it would compute size of 1, and then we go back, and then it would go to size of 2, and then at size of 2 it would look at size of 3, and then it would look at size of 4, size of 5, and then it would compute size of 0.
I guess we only look at every vertex once, right? So it's OV. But if we had to call size of 0 plus size of 1 and size of 1 and size of 2, then we'd that would be n squared, right?
So in let me think for a second. So this. I believe it's not linear, just the recursive one, but in a tree actually
If we have a very big tree,
I think it's
It would still be linear.
I think for a tree it might actually.
I mean, that's basically just DFS, right?
Yeah,
So-
yeah, I think it is DFS. Yeah. Okay, so yeah, so I guess like with a tree, it doesn't matter as much. But yeah, okay, so recursion works. In this case, you don't actually need to do a dynamic programming. It's just DFS. But the idea is you can also like, along the way, you just store the size once you compute it. Yeah, so you can create an array, let's say S of V, and once you compute it, you don't need to like look at all of the subchildren. But in this case, because it's a tree, actually, yeah, you're right, this just is the same as a regular DFS.
Also, I think we need to find for each V the size, right? So while
Yes.
size of 0 is O of V, if we had to find size of 0 and size of 1,
Yeah.
and
Okay.
that
but-
would be V squared. But with the DP, it would just be
Yeah, exactly. So one thing, what we realize is that when you call size of 0, it also computes, by the time it finishes and it computes size of 0, it's computed the size for every subnode as well. So notice that this computes all sizes of okay, so I guess we do need to we do need this array. I'll mention it. Yeah. No, it computes all sizes, size V in the recursive call. But we don't want to do this like after we call size 0, we've already computed all of the sizes. We don't want to call size of 1 again and then size of 2 again. So along the way, we want to store in an array size of V when it's done. So at the end of size 0, we actually have an array that that stores the sizes for every node. So this array is useful for storing, to store this. So thus we have an O of the n solution. So this is an O of n solution that finds the size of the subtree for every node. Okay, great. All right, so let's do a slightly more related to this problem, which is slightly modified. Will be, instead of finding the sum of distances from V to every other node, we just want to find the sum of distances from V to all the nodes in its subtree. So this is also a simpler version of the problem. Can anyone see how we might use a similar reasoning to this to do this version of the problem? So here, for example, the size, the sum of the distances from 2 to all the nodes in the subtree would be 1 plus 1 plus 1 is 3. Right, okay, so how can we use a solution method similar to this to solve this problem?
For I guess every path that comes to, let's say, a vertex V from one of its children, it has to first come to that child. So all the distances are just basically plus 1.
Yeah, so we can observe something similar if you have, if we have node V, and we've computed the sum of the distances from U1 to all of the nodes in its subtree, and same for U2 and for all of V's children, then that gives us a way to compute the answer for V. And the exact formula would be, let's say that I'm gonna denote, let's say I'm gonna denote this by subtree subsum V. This will be equal to so for all of the nodes in U1, it would be they would all be one distance one further, and similarly for all of these. So actually, it is just the sum for all of the children UI, and then plus the size of the number of nodes in a subtree of V minus excluding V itself.
Yeah.
So that would just be, I guess, size of V minus 1. Does everyone agree with this formula? Yeah. So first we can compute this using a single DFS and also storing the answer. And then we can also now compute this by another recursive call, and also again you store an array for this once you compute the answer. Okay, and what would be the runtime of this as well?
With DP, it would just be linear.
Yeah. With DP, or storing the answer for each V. This is just runtime is linear. V. because again, you only need to call subsum of 0, and that computes everything. All right, great. So that was the part where we were thinking about DP on subtrees. Now we're going to come back to this main problem. Okay. Only call subsum 0. All right. So what is the main sort of difficulty about the original problem, where you wanted to find the sum of distances from V to all nodes in the tree, compared to like these two problems that we just talked about?
So if some node is not in the subtree, it's above it, or not necessarily above, but
you would have to like,
it's not in the subtree. Basically.
You'd have to like go up, and then it would be like in the subtree of its parent or somewhere else. Yeah. So that's the tricky thing about this problem. So good thing we've computed these two things, so we know for the subtree what the answer is. So I guess the idea here is to look at how the answer changes when you move between two adjacent nodes. So for example, if I'm at node 0, let's say I've computed the answer for node 0, and I move down to node 2. By the answer, I mean the sum of distances from 0 to all nodes. Or I guess here it is same as subtree, but let's suppose you computed the distance from 0 to all nodes in the tree, and now you move down to 2. So the question is, how does the answer change? So I guess we can split this up into two parts. Let's say for node 3, how does the sum of distances, how does the distance change? Like when I look at 0 to 3 versus 2 to 3.
It reduces by 1.
It goes down by 1. And same for 4 and same for 5. And if I also had like some more nodes like this, like 6, it also goes down by 1. So we can see that, and also for 2 as well, because it's 1 and now it's 0. Okay, so what does that say about all the nodes in the subtree of 2? How does their contribution to the sum change when I move from 0 to 2?
All of their sums decrease by 1.
Yeah. So for each of these, when I look at, like, for all V in the subtree of 2, distance 0 V is equal to distance 2 V plus 1. And so when you go from 0 to 2, those distances, you would have to subtract 1 for all of those. Okay, what about, so that was in the subtree. What about the nodes that are not in the subtree of 2? I'm gonna just add a few more, let's say 7, 8. What happens to, say, the node at 8? How does distance of 0, 8 compare to the distance of 2, 8? So 0 to 8 and 2 to 8.
So distance of 2, 8 would be 0, 8 plus 1.
Yes. So in this case, it's the opposite direction. 0, 8 plus 1 is equal to this. And what about, say, I guess I will draw another node just to be, to show that this is actually holds in all the cases. Let's say this is node 9. Okay, it's not rooted at 0 anymore, but what about the distance for 9? From 0 to 9 versus 2 to 9?
It also increases.
Yeah, also increased by 1. So, is this true for all nodes outside of the subtree of 2?
Yes.
Yeah, exactly. So, so we see that for all nodes in the subtree of 2, when you move from 0 to 2, the answer, or the distance to that node decreases by 1. And for all nodes not in the subtree of 2, everything over here, the distance to that node increases by 1. Okay, so I guess we can write this, let's write this as like a mathematical equation. So let's say that I'm just going to write sum of v to be is the sum of distance from v to u over all u in the graph, in the vertex, all vertices. So let's say that more formally, let's say that v is the parent of a vertex u. So u is a direct child of v. So how can I write the sum of u in terms of the sum of v? So as we said earlier, what would the total change be as I move from v to u?
How many ever paths there are to be those many distances increased by 1?
Yeah, so I think you mean the, so which nodes increase by 1?
All the non-subtree.
Right. Okay, so those increase by 1.
Yes.
And
Those decrease by 1.
And these ones decrease by 1.
Yes.
So how many decrease by 1? What would, like, in terms of the things that we've written down?
I guess the size of subtree u.
Yes. So you would increase by size of u, and also decrease by the number of vertices that's not in the subtree, which is just n minus size of u.
Yeah.
And you can simplify it, it's 2 plus
Yeah.
2 size u minus n.
Yeah.
Okay, great. And so this is for any v, a child of u, where there's an edge between them. Okay, so now that we have this this equation, how can we finally compute the answer sum of v for all for every vertex in subquadratic time?
I guess this would also be linear, and so then you just do a sum of some u.
Yeah, so you would just call, so I guess, like, let's say that you've already computed the size for every node by this earlier. So I guess we would first have to find some, so you would first have to find some 0, and yeah, so you can directly do this, or you could also compute sum 0 just from a direct, like, DFS by itself as well. So you would first find sum of 0. That takes O of n. And then once you have sum of 0, then you can just do, yeah, you can do a DFS, but I think doing a BFS is a little bit easier because we just want to look at the child of each. So
Yes.
you can do a BFS from the root from 0, and that would compute, let's say at each point, it would compute sum for v, and then you would go to U1, it would compute the sum for U1, then it would compute the sum for U2, and so forth, and then as BFS. So the overall time complexity, time is O of n, because like everything that we've talked about here is O of n.
Yeah.
And what would the total space complexity be?
Also O of n?
Yeah.
Because
Because we just store like the size for each node and I guess like the subtree sum for each node. Yeah. Also O of n. So yeah, this gives us a nice way of computing the answer. So I guess to recap, there are two broad ideas that we learned today. The first is that a lot of times, if you want to do a DFS on a tree, and you want to compute something for every node, then you don't have to do the DFS starting from every node. You can just do it at the root, and if you store the answer, then computing the answer for the root also computes the answer for every node as well, which is what we saw here. And the second idea is, I guess, a little bit trickier. And in this problem, it was looking at how does the answer change when you look locally at some vertex and you move to a neighbor. And from there, we were able to see that you can actually express the answer for these two adjacent nodes in terms of simpler terms that we can compute in terms of subtrees, even though the original problem isn't actually, the original problem is finding the distance to every node, which doesn't directly appear to be related to subtrees, but by looking at this idea, we can find a way to compute it after we found these things for subtrees. All right, so that's yeah, I guess that's the end of this problem. Does anyone have any questions about any of the sub-problems that we solved or a general solution?
I think no, none for me.
Any questions? Yeah, Faridun?
Yeah, when doing the actual code on the very right, so for every find the sum of 0, it did that for every child of 0, we will do a sum of u equals the sum of v plus the.
Oh yeah, so for sum 0, I think I believe you actually can. In this case, because it's a tree, you don't need to. I was thinking for sum 0, you can do, you can just do like a very naive, like, you do like a BFS or a DFS at the beginning to first find what's the depth of each node to the root.
Okay.
And that you can just do with either BFS or DFS. Yeah. And the size you also compute a separate time with this. Yeah.
Okay, that's very clear.
Yes. Okay. All right. Yeah.
Thanks so much. Learned a lot.
Yeah.
No way. Great. Thank you.
Yeah.
Yeah, I guess, yeah, implementing this it's generally it's not too bad. It's maybe a little bit lengthy, but each of these boils down to either like a DFS or a BFS and like storing the answer in an array. So, yeah. All right.
Thank you, Roy.
Yeah, thanks.
Awesome.